Let me introduce first. Okay.
Hello.
Can you see my screen?
Yes.
Okay.
Hello, Yusuf. Hello, Yusuf.
Oh, hi, sir. How you doing?
Hi. Hi. How are you?
I'm good, thank you.
Yeah, I just came back to my home. Okay, and just a bit late. Okay, how are you? How are you, by the way?
I'm good. I'm good. I'm good. Thanks.
Good, good, good. Thanks, thanks, thanks. Ready, sir?
Yes, sir. Yes, sir. Good evening,
Yeah.
sir.
Good evening. Good evening. Ready. Good
Yes,
evening.
sir.
Ready.
Sir,
I joined
shall I
through
go ahead?
phone. Huh? Joined through phone. Okay.
Shall I go ahead,
Yeah.
sir?
Yeah. Please, 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 please.
Yeah. Good evening, all. Myself, KCS Reddy, and I want to introduce the today's speaker, Mr. Mohammad Yusuf Saheb, who is our alumni of BMS IT, and he has finished his graduation in year 2016. And after that, he has gone for higher studies, and he studied the Master of Science in Engineering and Industrial Management by 2018, and he got the intern in the Rolls Royce company, and then he has joined as a manufacturing engineering intern in 2017. And after that, he has worked for the Rolls Royce from the past to 2021, almost 9 months, and his designation is as a development engineer. And his work is mainly on Industry 4.0, how the market study reports and understand the significance, and as well as the tools which are available. And he is engaged in the corporate HSE team as well, and he has successfully completed the user acceptance testing on the plant shop floor systems. And also, Rolls-Royce Yellow Belt is also for the improvement of the project on the manufacturing system industry, and is now, I think, a green belt certified green belt quality engineer. And this is a little bit about him, but we know him from the past 5 years, and he's one of the toppers in our BMS IT. And I'm very glad to work in, Rolls Royce. That great achievement for Mohammad Yusuf Sahib. And with this, I want to hand over to the Mohammad Yusuf Sahib to continue his session on the holistic engineer of tomorrow. So thank you, Yusuf.
No worries. Thanks for that introduction.
Yeah.
So yeah,
Yusuf.
sorry. Yeah.
Yeah, just a bit of interruption from my side. Okay, now,
Mhm.
dear students, it's a great opportunity for all of us to understand about what's actually happening outside the market. Okay, so when you all go into the world, so here is a great opportunity. So in this regard, I wholeheartedly thank Yusuf for taking this time from to join and give inputs about the industry 4.0. I kindly request for all the students to get the maximum benefit of it. Okay. Again, I will thank Yusuf from the Department of
No
Mechanical
worries.
Engineering wholeheartedly. Please go ahead, Yusuf.
Thank you. So I know my introduction. I think I had talked to KCR sir quite some time ago. So there's been developments in my career as well. So I was a yellow belt when I talked to when I talked to KCR sir last time, but now I'm fortunately I've become a black belt coach. So which means for anything that needs to be around continuous improvements in corporate world, basically. I would be coaching them how to do your continuous improvement, lean engineering, Six Sigma, and SQC, all of that. And also, I passed out from the university in 2016, but I've been in Rolls Royce for about 5 years now. So, in different capacities, but as a full time permanent employee, it's almost 2.5 years. So, I think, and one of the things that I want to go through with you in this talk is I don't want this to be a very technical talk where we sit down and I talk to you about how does aero engine work or how does engineering itself happen in Rolls-Royce, because you'd be studying a lot of these concepts in your in your BE mechanical engineering program anyway. But what I want to use this session is to give you a brief introduction, definitely, about the technical side of Rolls-Royce. But at the same time, I want to make some information available to you, which can help you in your placements. So it's things which I reflect and say, if I had known this earlier on, it would have helped me basically plan my career better. So I've put a list of such kind of things together, and hopefully this session should be useful. The last 20 minutes or so I've kept for questions, but we might overrun because I've got quite some material to show you through, and I've got a really nice video as well, which I hope you'll enjoy. But after that, if you've got any questions, we can move into it. So let's get started. Yeah. So just what we're going to talk about today is we'll do a brief background of what I've done since my graduation from BMSIT, give you an overview of what Rolls-Royce is. Spoiler alert, it's not manufacturing cars anymore. So we used to, but we have sold that cars division to BMW in 1998. So right now, Rolls-Royce is a completely different company. It's not anything. It doesn't have anything to do with cars. The second bit is we'll go into a bit of a technical view. I know just to draw lines from what you're learning every day in your ME program and connect it to the corporate and the real world applications. After that, we'll just talk about how engineering fits into a larger picture. That is understanding what the context of engineering is. And from maybe 5 or 10 years ago, engineering has changed dramatically. So I want to bring out those points. And lastly, we'll talk about what the industry expects for engineers coming out of in this year and the next few years. So this will give you hopefully a head start as to what you need to focus on. So let's get into a bit more of the origin story. So I finished my engineering in mechanical engineering with in 2016. So and at that time, BMSIT didn't even look as green and colorful as it looks today. And major I think thanks to Praveen sir to do that. But it was a lot less greener. I finished in 2016, then moved immediately after I went to Leicester. And there in University of Leicester, I did a program called Masters in Engineering Management. And as part of that degree, I did a year-long internship with Rolls-Royce. So, and that was in 2018. I finished that off in 2018 and then moved into a permanent role in Rolls-Royce as part of the graduate program in 2019. So January 2019 was when I properly started my role in Rolls-Royce. And since then, I've moved around the business quite a bit because, I've just been experimenting with what I like. And a lot of the larger corporate companies give you that flexibility to find where you want to be if you're in a graduate program. But in 2020 onwards, I started my substantive role, which is basically substantive means your full-time permanent role. So you stay in that role for 2, 3, 5 years, and that's where your comfort zone is. So just a bit of an overview of what I've done as part of my permanent role. I started off as a manufacturing engineer in the external supply chain. So this is working with external suppliers. So Rolls-Royce does not make everything that goes onto an engine, but it outsources a lot of the manufacturing to smaller companies. So you need an ME to deal with all the drawings, the manufacture, design, and bits and pieces. With the external supply chain, and that's what my role was in a team called Fast Make. So Fast Make basically look after future engines. So the next big thing for Rolls-Royce is a huge engine called Ultrafan that will be released maybe the next year or so. After that, I moved into an area of Rolls-Royce called development and experimental. This is where we decide what requirements, what features need to be on an engine, and then the design engineers, they design everything, send the drawings to the manufacturers. The manufacturers make the part and then send it to development and experimental to test it basically. So we define what tests need to be done on that engine. For example, we say we need to test what happens to an engine if sand goes into it, or if ice goes into it, or if a bird hits the fan, or what happens when one of the engine loses power will the aircraft still be able to fly on the other engine? So different many kinds of tests are being done in experimental, and after that, based on those findings, we progress the design till it becomes good enough to be launched into service. So as part of that role, I became a black belt accredited lead. So what this means is you're involved in continuous improvement projects with deliver about anything from 500,000, which is 5 crore rupees, to about 10 crore rupees improvements, worth of improvements, and this can be in cost or time or just new processes. After that, I moved quite recently. In fact, I'm still in the process of moving, and I'll be starting this new role from January. But I'm moving into a production assembly and test, and this is your, you put your engine together and you send it off to Airbus or Boeing. And as part of that, I'm looking in the industrialization side of things, and what if you reflect, each of these draws a line to your different subjects in ME. So hold that thought, we'll go into it a bit more later. But in general, just a top view of what Rolls-Royce are. Like I said, they don't manufacture cars anymore, but what they do is they manufacture all your large jet engines, aircraft engines. The Rolls-Royce they're broadly divided in 3 areas. The most popular one is the civil aerospace. So all your large wide body engines, where you've got double aisles in your large aircrafts. So they design engines for that. And the main competitor is GE, but we own about 50% of all of the market for large engines. We also design jets for business aircrafts, and in defense, we are looking purely at all your defense aircraft, basically. Your fighter jets, for example, quite recently we won a contract for a B-52 bomber, and so those kinds of military applications are taken care of in defense. We also build nuclear reactors for submarines, which is a quite secret part of the business. So even people within Rolls-Royce don't know much about what happens in Rolls-Royce submarines. So it's a very classified part of the company. Then in power systems, we design all your power grids, huge generator sets. They also make ship vessel, marine vessels, power systems, their power generations, their engines. Then even some instances, we also manufacture your locomotive engines as well. So that's broadly what Rolls-Royce does in those 3 areas. I work in the civil large engines area, and in that we've got several engines. This is just a snapshot of some of the more recent engines we've got and what aircrafts they're on. So, for example, the Trent 7000, this is one of our newest engines, and that's going on to the Airbus A330 Neo. The XWB, that's our main highlight. So it's the world's largest at the moment. It's also the world's most efficient engine as well. And that's a very popular engine, and it's the only engine that's offered on the Airbus A350. You've got your Trent 1000 and Dash 10s, which goes on to the 787 in Boeing, which is also called the Dreamliner. You've got Trent 900, which is your 4 engines, huge double-decker A380 series of Airbus. And then we have got Trent 800, which is on the 777, 700 on the A330, again a very popular engine, and 500 is on the A340, again a 4-engine aircraft. That's quite old now; they're no longer in production anymore. Anyway, that was a really good, really short summary of what Rolls-Royce is and what I've done in Rolls-Royce. If you want to ask anything more specific about my experiences in Rolls-Royce, you can make a note. We can touch on that in the Q&A session. But let's get a bit more technical now. I'm not sure whether you've already studied about thermo. I mean, you would have done thermodynamics by the end of second year. You'd also go into the space of fluid dynamics and fluid statics, as well as some of the turbo machinery from KKN's. But you'll see that by the end of your third year, everything you've learned comes together. So they're not individual subjects, but they come together in any kind of application. And this is not specific to gas turbine technology. And we'll see that now, how they all mesh together in how gas turbine works. But before that, just need to understand what are the different parts of an aircraft engine. Now, this is a very, very simplistic model. This is the right side is a picture of an XWB. And this is how it looks inside. So up front, you've got all of this from this fan till this point. It's called the compressor module. All of this is compressors. At this point, the small bit you see here, that's your combustion systems. And then after the combustion systems, everything you see at the back end, that's your turbine system. So you've got compressor, combustion systems, and your turbines, basically. So what happens is when an engine is flying, the fan sucks the air inside, and then it compresses. So these blades are specially designed to compress the air as much as possible. And when that compressed air, it goes into the engine and it burns. And we'll see that in more detail in the next slide. But this is how a very broad overview of an engine looks like. So you've got your, and again, in each of these compressors, you've got different stages. Now, again, if you haven't already studied, you'll learn about pressure compounding, velocity compounding. All of that happens here. So, in different stages of compressors, the pressure increases and the temperature starts increasing as well, till it reaches a point just before it enters into the combustion. It reaches the maximum pressure, which can be physically handled within the case, and then it goes into the combustion, burns, and it comes out of the turbines, which is basically, again, stage. So you've got different stages of high pressure turbines, and then as it flows through the turbine assembly, it loses its pressure. So towards the back end of it, it's a low pressure turbine system. Now, each of these systems are connected to one another, and I'll show. And if you can see here, these long stubs here, they are called stubs or shafts. So it connects the compressor to the turbine. So, for example, the fan is connected to this IP compressor. Intermediate pressure compressor is connected to the intermediate turbines, and the high pressure compressors are connected to the high pressure turbines. So they've got almost two to three shaft systems inside, and you can see in this picture that they are connected to each other. So before we go into the core functioning from the technology point of view, just a few quick facts, to get you interested in how massive these engines are and how big, how powerful they are, basically. So just the diameter of this big XWB engine, it's equal to a Concorde. Now, I don't know if you've seen a Concorde before, but they used to be the fastest jet ever made, but they've been, because of technological and economic reasons, they were retired much earlier on. But the whole airframe circumference, the whole diameter of the complete aircraft can fit inside one XWB engine. So you can see for here, this is a man, and you've got this huge XWB engine on there. And the other thing is, so each of the fan blades at the front, I think every second, correct? Yeah, every second it sucks up to 1.3 tons of air, and that's equal to a tennis court, basically. So if you have a tennis court and all the air inside it, so imagine the whole of that air being sucked in every second into this huge engine. Then once it goes into that, each of these fan blades, at takeoff, it can carry a load of 90 double-decker buses. So if you look at BMTC, back in the day, there used to be a double-decker BMTC, and I don't think they do that anymore. So if you had almost 9 of those hanging off each of those blades, that's the kind of power you're looking at that goes into just at the front end of the engine. After it goes in, it hits these high pressure compressor blades and turbine blades after the combustion. So when it's taking off, that's when the pressure is maximum, the power is maximum. Each of these 68 high pressure blades, it generates you know the power of a Formula car. So if you've got 68, imagine that this aircraft is generating the power of 68 Formula One cars just at takeoff. And once it takes off, you've got obviously the pressure inside the turbine is they cross over 2000 degrees Celsius, and there's a lot of engineering that goes inside just to prevent the turbines and the components inside the engine from melting off. So it's a very intricate design that that the designers have made, which allows the temperature of those turbine blades to be less than their melting temperature. And a lot of times, even with the most advanced materials we have got for turbines, I think their melting temperature is about 1,400, if I'm not wrong. And you can see, because the temperature inside is over 2,000 degrees, it's very important that they make sure they understand how they cool those turbine blades, as well as how they how they design the coatings, the thermal barrier coatings on your each turbine blade. And again, when all of this happens and the burnt gases are pushed out of the nozzle at the back, the air leaves at the back of the engine at around 1,000 miles per hour. That's roughly about 1,600 kilometers per hour, and that's a massive force. So just some interesting bits to know, to understand, to give you an idea of how powerful an engine is. And this is not an easy. This is in fact one of the most amazing engineering feats that basically people have achieved. So with that, let's move into a bit more technical. I know I said that was technical, but let's go a level below. And when you're doing these problems, when you're doing fluid dynamics, or when you're doing turbo machinery and all these other sums and problems in your exams, you often come across these diagrams. And quite honestly, when I was doing my BE, we used to use these diagrams, but we couldn't make any sense of it, just because unfortunately, the way we learn is we don't try to apply what we learn in real world scenarios. And which is what I continuously encourage people, is that if you're learning technical concepts, although when you look at this, you have just two inverted trapeziums, but how do they actually work? When we say that the fuel is coming in and the temperature is rising and pressures are falling or volumes decreasing, it's as easy as going to YouTube and searching how a pump works, or how a turbine works, basically. So this is a very simplistic diagram of this. What you see here is what's being represented here. So until you look at this kind of picture, you'll never appreciate what kind of problem you're solving. And it just makes a lot easier if you understand visually what you're dealing with, basically. So again, you come to a lot of these inlet, these pressures and temperatures, and in our exams, it's just a statement saying that your ambient pressure was 101 bar, your ambient temperature was 35 degree Kelvin, and whatever. But till you understand at what point are those temperatures located, what is a turbine entry temperature, what's a turbine exit temperature, you won't enjoy the learning process. It just becomes another problem you need to solve, and another question you need to take off in your exam paper. So just try to relate what you're learning up front. So don't keep it towards the end. Relate what you're learning much earlier on during the learning process, and I can guarantee you'll enjoy engineering a lot more. But in any case, so purely from a working principle point of view, like I said, the fan, when it's rotating, it it sucks the air in, and it compresses it. Now, one of the key things which a lot of people don't know is that um, all this air that's being sucked in, not all of it goes into the whole compressor and turbine assembly. A lot of it is just bypassed. So, for example, in the XWB, the bypass ratio is almost 10 is to 1. So for every 10 parts of that air, uh, only for every 11 parts, only 10 parts go in and only one part goes in. So if you want to put it in terms of percentage, of all the amount of the 100% of the air that goes into the fan, only 10% of it goes into the aircraft engine. The rest 90% is flows around the engine, and they produce thrust at the back of this. So the thrust is a component of both this bypass air and this nozzle pressure which comes out. So that 10% of the air that goes in, it gets compressed through various compression ratios. So the fan is your lowest pressure, so it's called LP systems, and then it goes through a further few stages of low pressure compressor systems. Then it goes into an IP. Some of them some of the aircrafts have IP pressure, some don't, but some XWB, for example, it has an IP system right here. So again, pressure increases, the volume decreases, and as the volume decreases, temperatures start to rise. Then in the high pressure, this is where the air is pressurized to the maximum that can be held here, and then after that, it's sprayed into the combustion chamber, and the fuel connects here, and it sprays the fuels into tiny droplets, in almost like a mist, into that air, and then you've got a spark plug which ignites it. When it ignites, because of the high temperature, there's a huge pressure gain that happens there, and that literally pushes the turbines. And because of this is where you have the maximum pressure, so these are called high pressure turbines. And as the air pushes these turbine blades, this turbine blade is connected to your high pressure compressor system, and when this turns, it drives this. So it's almost like you've got air coming in, it's burning and driving the turbine blades. The turbine blades then in turn are driving the compression system. So it's almost like a loop there, a feedback loop. As the air moves through the turbine systems, after it goes past the high pressure turbine, it goes into an intermediate pressure turbine where the pressure drops a little more. And again, these rotate at a slower speed compared to this, obviously because the pressure has dropped, which is why the speed here is also lower. And then finally, towards the end, you've got the low pressure turbines, and this low pressure turbines drives the fan, which is a low pressure compressor system. And then the exhaust gases are expelled out, and that gives a percentage of that thrust as well. So this is how a gas turbine works. Most applications work similarly. The differences you would find is the design of the combustion systems, how many compressors are there, whether you have two compressor systems or you have three, HP, IP, and LP, and also the fact that how many compounding stages are there within each of those low pressure, intermediate pressure, and high pressure systems, both in compressors and turbines. But the general principle is the same for pretty much everything, all your gas turbine applications. Again, I told you 90% of the air goes in over the engine, only 10% goes inside. This is for your large, huge aircraft, passenger aircraft. But depending on the application, they vary this level. They vary this bypass ratio. So if you look at efficiency, the higher the bypass ratio, that is more of the air that goes around the engine, higher the efficiency. So if you need less air to run this whole system, it means you're more efficient. But sometimes if you're looking in, this is turbojet, if you're looking at a low bypass jet aircraft, you need air to go through really quickly. So you have a low bypass system so that the majority of the air is pushed into the combustion system. This is what you find in your military aircrafts. You've also got a turbo fan and a turboprop, and this is where you've got an actual physical propeller up front. So you don't have it like an enclosed engine, but instead you have something like, you used to see these on those Indigo aircrafts or Deccan Airways back in the day. Again, turboshaft, it's similar. It's used in helicopters. A ramjet is used in supersonic aircrafts, where it's the whole of that. There's no compression system. It's already flying at a very high speed, so the air goes in compressed and just goes inside the combustion. There's a bang, and the aircraft is propels forward. It's a very specific application, but you find different flavors depending on what the bypass is on different applications of aviation. So this was about all the technical side of things, and let's move into a bit more general discussion now. I want to stop and ask if there are any questions, but just going by time, I think I'll just finish off the next two bits, and then we can open it up for questions. Make a note of them if you've got it. But let's go into the holistic side of things now. Holistic basically means well-rounded. Engineering traditionally, when you sat down for CET, you would decide, okay, I want to be a mechanical engineer, or someone says, no, I want to be a software engineer, and then someone else says, no, I want to be telecom or electronic and electrical, and so on. So everyone goes into these disciplines thinking that for the rest of their lives, for the rest of their career, that's the area they'll be working in. So if you're doing mechanical engineering, what the expectation is that your interests and your future career will be something around, making things or designing physical or mechanical components. But unfortunately, things have moved on. So, and one of the good things, especially what I've seen after coming to the UK, is in the Indian education system, the first 1 year we do of general engineering. So basically, we look at all the different disciplines in engineering, and we do our first year across that engineering discipline. So that helps us understand the different disciplines within engineering. But one thing we don't do well is how we connect each of those together. And that's what I want to try and bring out in this section. The other bit is engineering isn't just numbers. It's not just formulae that you pick up from the logbook or from the design book, and it's more than calculations. What I've noticed going into industry is everything, when they start the design process, they try and relate it back to first principles. They try and relate it back to nature. So, for example, what you see at the left here, at the top left, is it's a transport aircraft called the Beluga, and it's what it carries inside is it is used to transport the wings of an A350 and A380 from I think UK to France or Spain to France, because France is where the main assembly, the whole assembly unit is for Airbus. But all the different parts are made all around the world. So they need to transport it to France, and they use the Beluga to do it. This was inspired, this design was inspired by looking at the blue whale in nature. So you can almost see an eye there. And there's a species of the whale called Beluga, which is why they have named the aircraft as well. So this inspiration came from nature. Again, a lot of the aircraft wing modifications we see is when new aircrafts come in, they try and go back to nature and see what are the different kind of wing designs, wing structures on different birds, and they try to use those principles and engineer them into physical products. And at the same time, you've got something new coming in. I don't know if it's coming, but it's definitely a concept design which Airbus have showed, is something called a bird of prey design, and this is how that aircraft looks. And you can almost see that it's almost like a bird of prey. So a lot of the inspiration comes from nature. It comes from first principles, from really basic understanding, and that is why it's necessary to understand why what are what's the fundamental knowledge you need in your field. So engineering is basically applied physics. So often you need to understand basic um, concepts in physics to be able to actually do good engineering or become good engineers. So if it's just a matter of, oh, you've got a moment, you've got a distance, and what's the force with which a bar bends, and if all you're doing is just applying formula and calculations and not understanding why does it actually bend, then you'll not truly appreciate what engineering is about. It just becomes one of those another subject you learn and then you forget just the next day after you finish your exams. So engineering is a lot more than those numbers and calculations. And the next bit, I just want to try and tell you what kind of organizational structures exist in a technology organization. Now, another interesting bit is engineering companies, uh, as they progress, they no longer call themselves as engineering, they call themselves as technology, because the industries are realizing that that engineering on its own can't achieve much, which is why the whole concept of moving into a technology organization is becoming the new trend now. And within a technology organization, and this is broadly how Rolls-Royce is structured as well, you've got a whole sub-organization within Rolls-Royce that deals with design. And in design, you talk about, actually physically designing it on various CAD softwares, and then you're doing analysis of those design systems of airflow systems, and doing your aerothermal stress analysis and all of that. And then you talk to other people, you talk to manufacturing, you talk to repair through DFX. So X means it can be DFM, or DF, design for manufacture, or design for engineering, or design for repair. So X can be any of these different things. And finally, once you have designed all of that, you've tested it virtually and simulated it, you build it physically, and then you test it on an engine in real life. And that's where you do all your development and experimental learning. The other side of the organization is the manufacture bit. Again, to be a profitable company, you can't manufacture everything that goes into an engine. In fact, an engine has about 30 to 40,000 parts, and out of that, about 80% of those parts are made externally by other people. Rolls-Royce only makes 20% of an engine component in-house. And these are the critical IP ones, the main intellectual property parts, like the design of a turbine blade, the design of your compressor blades, the design of your combustion system. All of that is made by Rolls-Royce, because that's very specific and very research-intensive parts. Everything else, all your pipes, all your fuel pumps, your gears, they're all manufactured by someone else in the external supply chain. So in manufacture, you've got a component of making it in-house within Rolls-Royce, and then you've got also buying it from the external supply chain, which is what one of my role was. And then finally, once you have made all the different components, it goes into assembly and test, and that's where they put all the engines together. I mean, all the modules together into an engine. And after it's been sent off to the customer, they put it onto an aircraft, and Rolls-Royce continues to monitor how the engine is performing. So you have a lot of data that's coming into Rolls-Royce through digital means, and we keep monitoring them. And at specific intervals, if something goes wrong, they do on-wing repair and maintenance. And at regular intervals, similar to your bike or your car servicing, they have to take the engine off the wing and bring it into Rolls-Royce to get it fully serviced and maintained. And that's what happens in overhaul services. Now, if you look at Rolls-Royce and the kind of product it builds, it feels like it's a very mechanical engineering, very manufacturing-oriented industry. But when you look into each of these components, we find that it includes engineers from across the spectrum. We have engineers who are involved in commercial, we have engineers who are involved in logistics, in digital, you're involved in repair and maintenance. You've got people involved in process simulation and parametric studies, as well as doing systems engineering. So you've got flavors of different kind of engineering in just one organization. The other bit is, again, when you look at an engine, everything feels mechanical, everything feels manufacturing related. But something to bring out here is that an engine on its own, just with its mechanical components, can't do anything. You need an electronics controller, an ECU, an engine control unit, which basically will control how the engine runs and responds to any commands sent from the cockpit. And that involves electronics engineering, all the circuitry that goes within the different engines. And there's millions and millions of electronic leads that come out. And for that circuitry, you need electrical engineering. And sorry, I seem to have mentioned it twice. And then if you have anything related to materials, we're talking about materials which need to withstand 2000 degrees Celsius. We come into the space of materials engineering. All the data that needs to be collected while an engine is running, so that we prevent any disasters. Because if something goes wrong on an aircraft, you're not talking about, all right, let's park it in the side and change the tire. It's not a car, it's in the air. If something goes wrong and an aircraft crashes, it's a major issue. You have people dying in the, about hundreds and hundreds of people dying if something goes wrong. So we have to constantly monitor an engine, and that's done with data sciences and computer and software engineering. At the same time, if you've got an electronics ECU and you've got a mechanical product, both of them are connected through software engineering, how it performs, and that is through your engine softwares. So a lot of it is multidisciplinary. It does not limit itself just to one field. So just because Rolls-Royce makes engines and all the engine concepts of working concepts are based on mechanical engineering, doesn't necessarily mean that if you know mechanical engineering, that's sufficient for you to be a good engineer. So this is where you need to start drawing lines between different disciplines and at least becoming aware of what other disciplines are about. So with that, we'll just go into the engineer of the future. And this is one of the things I hope will help you plan what your next steps are, because third year is the right year where you need to plan. Because by the end of after your seventh semester, you're already a bit late, because if that is when you need this third year is when you need to get your feet moving towards your future career trajectory. So from a Rolls-Royce point of view, and a lot of companies are again looking along similar lines, whether they are aviation or automotive or even general manufacturing or mechanical industries. They are looking at how can we become more electrified. So how can we bring in more electrification? So in Rolls-Royce, it means electric flights or hybrid electric flights. In automotive, you already see a lot of Tesla and other electronic battery-based cars coming in. So electrification is one of the key topics, key trends of the future. Then the other bit is digitalization. Now, digitalization is another huge area which has a lot of potential, and I can't state this enough, because literally every company is talking about digitalization. The way the world is moving now, you have seen recently Facebook is launching something called Meta, and everything's going to be digital. So it's almost like you're living a life in the digital world. So and even in industries, it's a lot cheaper to design, test, and simulate something digitally than to convert it into a physical product, manufacture it, test it, and then it all burns up or breaks or explodes, and then you're like, oh no, what's gone wrong? So you've lost all the product, you've lost all the materials, all of that effort and time. Whereas if you do all of that digitally through your CAD/CAM softwares, through your CAP softwares, it's just a lot more cost effective. So with this, people are moving heavily towards digitalization and making maximum use of data generated. So that's one of the key hot topics in the future. And all your discussions about automation, AI, big data, Industry 4.0 fall within this digitalization strand. And this is one of these evergreen areas within engineering, which will apply to all industries, irrespective of your field. So you would need digitalization in mechanical, in civil, in automotive, and basically every field that you can think of. You have some sort of digitalization taking place. And lastly, there is a you'd have read in news, and you have come across, or you would have just visited Delhi. There's a huge drive for climate change, and it's impacting everyone. And there is a lot more awareness coming out from the fact that we are basically heavily polluting the earth. And in the next 5-10 years, there's a massive risk of huge islands drowning, or increased global temperatures and so on. So there is a massive drive for how can we work to climate control. And this is not just from moral ethical point of view. There is new legislations, new legal demands which these companies have to fulfill, basically. So if the FA, which is the flight agency, or the EASA, which is the European Agency for Aircraft Safety, if they make the rules and say, well, you can't produce more than X tons of carbon dioxide, and if that aircraft is producing more than that, they can't fly it. So there's a legal obligation, because if you fly it, you're breaking the law. You'll be penalized for it. You'll face legal issues. So it's becoming one of those areas where a lot of drive is coming in. So environmental engineering has become a big topic. Renewable energy engineering is becoming quite significant in the next few years. So that's about the future. But just on a personal level, how do we develop as engineers? There are three broad types of engineers. Every engineer that you come across falls within these three types. You've got someone who is really good at something. They are an expert, basically, at one particular field, and that's what an I-shaped engineer is. They're an expert at one thing, and they're called specialists. And then you've got people who are aware, who know a lot of things but not in depth. So they know a little bit about mechanical, they know a little bit about civil, they know a lot about, and this is not just restricted to engineering, because if you want to be a good engineer, you also need to know the world you operate in. So you need to know about safety, you need to know about the commercial side of things, you need to know about industrializations, you need to know how the markets work, you need to understand how a business works. So business analysis, marketing, communications, commercial aspects, these are all different things that an engineer needs to be aware of as well. So you have got people who know all those fields in a little bit. So they've got a very broad understanding of different disciplines, but they don't have expertise in any. And those are those people you call generalists. Sorry. And the third type, and which is what I want to push your thinking towards, and again, this is what companies are trying to develop their engineers into, is something called T-shaped, where you are an expert in one or two fields, but at the same time, you have a cross-disciplinary competence. So you are able to understand commercial bets. You don't need to know everything about commercial. You don't need to go and say, okay, this is how you need to make money. This is how you can sell this product. You don't need to know that level. What you need to know is, how do we make money, or how does say, for example, if you're working in Wipro, how does Wipro make money, and how does the work I do fit into that? So that kind of knowledge, as well as some experience in different parts of the business, not just engineering, is where you develop the head of the T, this cross-disciplinary competence. And when you finally find something that you enjoy, that's when you build the stem of the T, the way you build your deep subject matter expertise, your deep understanding of that field. What happens a lot of times is some people they find an area which they think they like, and they jump into it, spend a lot of time building that experience, and then 5 years later they realize that there's something else that they hadn't looked at and they would have enjoyed a bit more. There are also people who, they try their hand at everything their whole life. They don't build any expertise, and then after 10 years, when they want to jump companies or move into a different market, they're not able to find roles because the company says, well, you've got a bit of everything, but you're not good. You're not really good at anything, at any one particular thing. So that's why being only a generalist also hurts your career prospects. So my advice is, you would ideally, just as a fresh graduate, you would start at building some form of generalist experience. So you try out different things through your internships, through your graduate programs, through your entry level jobs, and through that initial experience that you build, you start identifying what areas you really enjoy. And after when you have identified that area, you start building that expertise. You try and find projects within that area, talk to your managers, talk to your career coaches in that company, and build your expertise in that level. And that's when you become a good T engineer. And this is one of the strongest types of engineer that is available in the job market. So if you apply to a company and you can demonstrate that I've done all of these various things, but I've enjoyed this particular field, and that's where I've built my expertise. So it shows that you are a well planned, and you're a very logically oriented person who knows what they're doing, basically. So something to think about when you're deciding your career forward. We've got 10 minutes left. I'm going to finish this off really quickly and then open it up for questions. There's something called a Dunning-Kruger Effect, which I just wanted to bring out. Your learning is a commitment. It's not a one-night thing. It's not one of those things where you just you spend some time, you get bored, and then you move out of it. No, a lot of times learning is a continuous process. You have to stay committed, and especially when we pass when people pass off engineering degree programs, when you get your BE in your hand, you're at this point where you feel like, oh, I've studied all these subjects, I know everything, I can just go in and tackle whatever, I'm fit for any job there is. And because of that, you have people who have just completed their engineering and then applying for management positions, and they don't get it, and then they're disappointed, like, oh, I'm so good, I've done so much in life, why am I not being selected for management positions? And at the same time, you have people who do an engineering degree and then jump into an MBA program, and then think that they're automatically eligible for a manager's position just because they have an MBA. Again, even by hook or crook, if you go through influences and pull strings and you get a management position, just getting a management position isn't good enough. You have to be good at your job, because if you're not, people will realize that you're not fit for the role, and that's when you have people leaving the team or leaving the company or just not performing right. So to do that, you need to understand and know where you stand. So when you start, and this is where I encourage people, especially in your third and fourth years, to do as many internships as possible. Because when you start doing your internships, you start going on this journey where you feel, you start to understand that there's more than what you know. So when you start applying your engineering knowledge, you realize the gaps in your learning, and there might be times where it becomes difficult, and you reach a point where you feel like, what, engineering isn't for me. I can't do engineering. I'm going to go join some other field, or I'll start doing something else. But what happens is, as you build your knowledge, you come to a point where things start making sense, and after that you come to an appreciation that what you learn isn't always enough. You have to constantly be learning and developing yourself. So again, something to keep in mind just when you're finishing off. Key takeaway is, make sure you get started on this curve as soon as possible through your internship, through work experiences in your semester holidays. Lastly, before we wrap up, is some key things I want to make sure you have in mind before we leave. Is yes, you are mechanical engineers. Yes, you think you will be dealing with everything around manufacturing and design, but the truth is, you will need a lot more than just your core mechanical engineering skills. Try and start building some understanding of uh, a language, one language at least. Try and start building your skills in, say, for example, MATLAB or Python or C Sharp or C++ or Java, anything, just so that you are IT adept. Because, like I said, the future is even mechanical engineering is moving in a lot into automation, into digital, and this programming and IT skills helps a lot in that space. So it makes you a lot more employable when you sit in front of an employer and says, "Yes, I'm a mechanical engineer, but I know enough to work digitally as well." The second bit is, I think, and this is one of the key problems that a lot of people don't get placed as well in their final years or third years, is language and communication skills. So can't stress this enough. Unfortunately, the world we are operating in is based around English, and I would encourage people to build their English competencies. Give more presentations, and I'm sure third and fourth year have a lot of opportunities where you present your papers, where you do technical workshops, technical presentations. Make sure you use as many opportunities as you can through that, because you can read a book and say, all right, I'm good at English, but that doesn't happen. You can learn words in a dictionary and say, oh, I know all these words, so I'm fancy, I'm posh, I know all these I know all these English words, okay, I'm good at language skills. No, it doesn't work like that. You need to actually practice through your presentations. The third bit again is be aware. Talk. Have. I'm sure you have friends across disciplines, but most of your conversations with friends will be where's the next party, or which next pub you're going to, or where's the next trip, or when is the Goa trip, when all those kind of talk conversations. But make sure you have set aside some time to talk about what their engineering discipline looks like. You don't need to go into detail, just to understand what are the different things they that are involved in related disciplines. Work experiences, again, third, fourth, in fact, yeah, as early as possible, as many times as possible. Try and get experiences that you from different companies. Just and so they don't need to be advertised. You can just call up small companies and say, look, I'm a BE student. I'm interested in doing a work experience. Can I come and work with you? Even if it's low salary or no salary, the key thing that you need here is experience, not money. So a lot of people are put off because that internship isn't giving them enough money. So they don't want to waste time. But that's not how it should work. Make sure getting experience is the priority here. And again, when I say experiences, I don't mean asking an uncle who owns a factory to just send a recommendation letter so that you can put it onto your CV. What I'm talking about is actually physically working in an industry anywhere, basically. Again, realistic career aspirations. Like I said, don't finish your BE program and think, okay, I'm going to be a manager in my first role. Have a career, realistic career aspirations. Think about what you're going to do next and what you want to do next. And this is the right time, because, again, towards the second half of your final year, it's already getting a bit too late, because that's a lot of people don't have a plan, finish off engineering, and then they're in a bit of a crazy situation where they don't know what they want to do next, especially if they haven't got a placement sorted out. Also, if you don't want to go into computers, into a computer-based industry, if you don't want to go into softwares, don't force yourself into it. Maybe for a short period of time, just to get some experience sorted off. I would recommend. I would suggest that if your interest is mechanical, and I know core jobs are difficult to come by, but just because the opportunity isn't there at that point, I would advise not throwing it away completely. So always, even if you're working in an IT company, keep an eye out for a core mechanical or manufacturing based company if that's where your interest is. And sometimes you have to take a risk. So take a calculated risk and think, don't let your aspirations go to waste just because of circumstances. The last final point is planning your journey. Now, immediately after engineering, some students they know that they want to get into a job immediately, so placements is the way to go. But do consider postgraduate study as well, especially if you want to try something more specialist and you know what you want and what your interest area is. So you can do your masters either in India or you can go outside. Again, each of the other countries outside India offer different experiences, so do a bit of research, and this is the right time, because if you want to get into a postgraduate program right after your masters, you'd need to start exploring universities. And in fact, if start applying at least a year before if you want to get into some really good universities. Also, graduate programs. Now, this isn't common. I don't know why the awareness isn't there for graduate programs, but a lot of companies offer something called graduate programs. All you need to do is just a search on Google, and you'll find graduate programs, really good ones, which basically are meant for entry-level people. And they're a good way to get your foot into the company. I would recommend having a look at that. Lastly, a lot of students, again, they finish their engineering and then they move into building their own business. That is again quite an interesting way forward. So if that's your your interest, again, planning early is your key, because you get a lot of government grants, you get a lot of support from existing you've got bank schemes for entrepreneurship. And if you want to do something right after your engineering, you'd have to look into those early on, and that application can take a few years to get it all processed up. So you don't want to be sitting around and waiting for things to happen. You would have to go ahead and make them happen, basically. So with that, I finished the topic. I'm quite aware that we just hit 2 o'clock. So I'll be on again. I'm happy to stay on. But if you've got any questions, feel free to shoot forward. I had a video to show you, but it's on YouTube, so you can have a look at it. It's the area I'm going to be working in. It's a very interesting video. It's called, if you just type Rolls-Royce Assembly XWB, it's a video of how the XWB is assembled. So a really interesting video. It's about 3 minutes. I want to have time for questions now, so I won't play it right now, but I would recommend just after the session, have a look. It's pretty interesting. So with that, I will wrap up. So if you've got any questions, feel free to shout out. And yeah, thank you and thank you to KCR sir for the HOD sir as well, for putting together this whole this alumni session, basically. And it was nice to catch up with the new batchmates as well.
Yeah, any questions, please? If you have any questions, please ask.
Good afternoon, Yusuf sir.
Hi Shashank.
I think it's around 2 to 2:30 there in UK.
Yeah, it's 2 o'clock.
Okay, which year did you went for internship in Rolls-Royce, sir?
So I finished in 2016 and did my master's immediately afterwards. I started applying for roles in 2016 itself. So I started my internship in 2017. So it's a 1-year program for masters in UK. So I finished my master's around May 2017, and June 2017 I started my internship in Rolls-Royce.
Sir, did you do the internship in UK or like in German or Spain?
No, in UK. Usually it's within the same country you're doing your masters in.
Sir, what is the current software used by Rolls-Royce, sir? Like Sigma 6 or CATIA or AutoCAD?
Um, See, the thing is, we use so many softwares. It's difficult to say we use this and not that, because depending on application, we use a lot of different. So, for example, a lot of the design is done on Siemens NX softwares. A lot of it is done on some of them are done on AutoCAD. Uh, so it's difficult to say this is the one particular software. Lean Six Sigma isn't a software; it's a methodology. Uh, so it's how you approach a problem, and if you have heard of DMake or DMADV methodologies, that's what Lean Six Sigma is. It's about quality tools and not a software.
Yeah.
Yeah.
And can you say about living cost in UK per month for a normal person?
Um, Again, depends. So it could be anything between, it's roughly about 50,000
Like
rupees.
for students?
Yeah, so that's what I'm saying. So you can expect about 50,000 rupees per month for living costs. But a lot of times you get scholarships which help. The fees itself can be, again, depending on the university. If you want to study in like the top universities, you're looking at 20, 25, 30 lakhs for 1 year, just the fees. But if you're okay with mid-tier to lower tier universities, you're looking at maybe 10 to 15 lakhs per year. And again, it doesn't really depend on what university you're doing. It really for to apply for internships or jobs, it really depends on how good of an engineer you are. So I wouldn't bother too much about what university you're studying from. But yeah, approximately you're looking at around anything from 400 pounds to 500 pounds per month. So about 40 to 50,000 rupees.
Okay. And is Rolls-Royce Q4 been ready? Like they're being electrified now. Like Q4 is the new brand, I think, like a new car.
So that's what I mentioned, Shashank, at the very first bit of my talk, is that we don't make cars anymore. So the cars business is owned by BMW. It's got nothing to do with Rolls-Royce. It's a bit of a funny story, because Rolls-Royce sold the cars division to BMW, but they said they won't sell the brand name. So because of that, Rolls-Royce retained the brand name for a very long time. But because the Rolls-Royce cars are known for their luxury, for their engineering, when BMW bought it, they didn't want to change the branding, so they kept Rolls-Royce as the brand for their cars. But it's got nothing to do with Rolls-Royce aviation or the technology company, basically.
Fine, sir. Thank you.
No worries.
Yeah. Any other questions, please? Yeah, I think if we don't have any questions, we can close this session.
Yusuf?
Yeah, yes, sir.
Yeah, it's a very excellent presentation. Very, very, very well covered with all the topics. Now, I just want one thing that you need to address the student. So, what is that you see in the future with respect to the importance of this Industry 4.0? What aspects of Industry 4.0 is going to be more relevant for the students to know? Just your suggestions to our students regarding Industry 4.0.
Okay,
Just
fair
as
enough.
I think you can take some time on it.
Yeah, that's fine. So going one step back, say you need to understand what Industry 4 is and what. So some people call it the fourth industrial revolution, or common term is Industry 4.0 and big data. But the just to understand what Industry 4 is. So if you look at how manufacturing has progressed, the first bit is you've got your Iron Age and your Bronze Age, when you used your iron tools and bronze tools. And then you had your first industrial revolution with the discovery of wheel, and which steam engines coming into place. And then the second revolution was around the full use of steam engine applications into industry. So that's where your textile industry started using automation through steam engines. Your third industrial revolution was with the electronification, where you've got your electronic ECUs, your programmable controllers coming into place. So that's where manufacturing is enabled by electronics, basically. Now, the fourth one, the people who write the whole research about saying that this is just a continuation of the third one, but some say it's the fourth one, but you're not going to go into that. The interesting bit to understand is the fourth revolution or Industry 4.0 is everything to do with data. What people have realized is they have been manufacturing, for example, if you take a cars industry, they have been manufacturing Mahindra XUV for 10 years, for example. And they have 10 years worth of data that they don't use at all. So where are the problems going wrong? Where are the machines going wrong? What are the issues with quality? All of that is there in that 10 years of data, but you're not making use of it. So Industry 4.0, what it tries to do is try to use all of those available data and create a digital environment for that data to be analyzed. So when we are talking, the moment we start talking about digital, it includes everything about automation, about artificial intelligence, and again, in all of this, you have different subsets, different fields within these areas like machine learning. You've got robotics, you've got robotics and automation, things like that. There are also data sciences now. Industry 4.0 also includes data sciences. So when you're talking about big data and analytics, and this is going more into the commercial side. Sometimes a lot of it is not even engineering. It's a lot into commercial and project management, where you're looking at past data to predict what the quality or what the future trends look like. And people do that through big data and using existing data sets and put them into analysis softwares like Power BI, into simulation softwares, and they try to predict how the performance of an engine, for example, will be without physically building it. So a lot of the topic I talked about, where we are talking about simulation and analysis, stress analysis, performance analysis through digital means, that is included in 4.0. So in the future, if you say you want to be capable of, if you go into an industry, and this is what I meant, in the world is changing, digitalization is for Industry 4.0, basically. So if you want to be reliably employed in the future, you need to pick up on these trends. You need to have knowledge about what big data. You need to start looking at and a lot of it, again, unfortunately, it has an overlap with programming and IT skills. You don't need to know core programming, but at the same time, you also need to know, for example, how do you use Excel to process huge data sets? How do you use Power BI to process huge data sets? And that's how the future is. You need to, the key areas will be, for example, from a mechanical engineering point of view, automation, robotics, artificial intelligence. In artificial intelligence, you have got different flavors like machine learning, cybersecurity, and then computer networks, and so on. Yeah, those are the key areas I think I would suggest having a look at. Does that answer the question, sir?
Yeah.
Yeah.
Definitely it is covered. Okay. Yeah.
Yeah.
It was really interesting, Yusuf. A wonderful talk. You have covered all the aspects right from their basic thermodynamics. Okay.
Yeah.
And you have touched upon how the learning should happen. Okay. That is application. You have talked
Yeah.
about that. And very interesting thing that at the end you have talked about what is that they need to be. Then that you talked about a T-shaped individual. Okay, so that was very great, and we are very happy that you could able to spend your useful time with all of our students to know better and to plan their future according to the changing the market as of now. Okay. So I take this opportunity to thank you, Mohammad Yusuf, for your the excellent presentation. The competency and the confidence is really extraordinary. So we are happy. We are overwhelmed that we are very happy that you are our alumni. So great. That's very great. And thank you, dear students, for all your constant presence here. And we'll place this on the YouTube channel also. So have a look at the have a watch on this video. So basically, at the last 2-3 slides, it was very wonderful. It gives you a great exposure for you that how you should plan your future. Okay. So I take this opportunity to thank you all, and very importantly, I like to thank Professor KCS Reddy for taking the initiation and taking pain to make sure to connect the best of the best alumni to our the students, right? So thank you, Professor, for your the wonderful organization of this particular program. Okay. So thank
Thank
you,
you, sir.
thank you all. Ready, sir? Can we close it?
Yes, sir. We can end the session.
Yeah. Okay. So thank you all. Have a nice day. Have a nice weekend, Yusuf. Have a nice weekend.
Thank
Enjoy
you,
your day.
everyone.
Okay. Thank you.
Take care, everyone.
Thank you.
Bye.
Bye bye. Bye. Thank you, students.